of NEMA. Okay, I'll switch to English now. This is an overview of some of my projects that I worked as a PhD researcher, as a postdoctoral researcher at UCL, with a list of these wonderful people, Nicholas Achilleos, Patrick Gio, and Chris Sarich. So the general topic is how to construct some models of the magnetosphere of Jupiter. This will be mostly tutorial style, so just to highlight the differences between the terrestrial magnetosphere and the Jovian magnetosphere. Using these models, a couple of applications that we can use these models, and then I will finish the talk by mentioning some upcoming space missions. So just to be on the same page, when we talk about magnetospheres of any object in the universe, we talk about the region where the magnetic field of this object is dominant. Of course, when we talk about planetary magnetospheres, the magnetic field of this particular planet is dominant in this sense compared to the solar wind or the stellar wind of any other planet. Of course, in astrophysics, we like to define boundaries, but quote-unquote boundaries because they're not sharp transitions. There is a region where the solar wind pressure is gradually balanced by the planetary magnetic field and maybe some other sources of pressure. And regardless the exact object, we can understand and we can observe some common features. For instance, the bow shock, the main part of the magnetosphere, the magnetosheath, the magnetotail, and so forth. Maybe you have seen some interesting shapes of the magnetospheres, this very well-known pattern of magnetic field lines in yellow being washed away by the solar wind. But let's make an exercise. Let's start from the smallest magnetosphere that we know, Mercury. And let's zoom out. Now the entire magnetosphere of Mercury fits inside the Earth. Let's do the same exercise again. We zoom out, the entire magnetosphere of the Earth fits exactly inside Saturn. And if you do the same exercise again, the entire magnetosphere of Saturn fits in the inner magnetosphere of Jupiter. Of course, if you see these shapes, they seem very much alike. You see a transition region between the solar wind and the magnetic field. You see the magnetic field lines being dragged away. You see a magnetotail and so forth. But as I'm going to show you, things are quite different for the gas giant. So our first order approximation would be, okay, let's define the boundary, the bow shock or the magnetopause. We have the pressure of the solar wind, the dynamic pressure due to its velocity, and we also have the magnetic pressure from the magnetic field of the planet. So a first approximation would be, okay, the magnetopause is located at this point where these two pressures are equal. And if you do this exercise, let's say for the Earth, and you predict the location of the magnetopause, this fits quite well with the existing data, around 10 terrestrial radii. If you do the same exercise now for Saturn and Jupiter, who of course have like magnetic fields hundreds or thousands of times stronger than the terrestrial magnetic field, your predictions are off, especially for Saturn. The prediction, if you assume that the magnetic field of Jupiter is a very nice dipole, you will predict a location of the magnetopause at 46 planetary radii, but on average, the magnetopause of Jupiter is at 75. So our prediction is quite wrong. And this is also shown by this green line. You see up to, for Mercury and the Earth, we're doing a quite good job, but that's it. So we're missing something. And one thing we're missing is that in the magnetosphere of Saturn and Jupiter, we have hot plasma. So plasma with energy much higher than its kinetic energy due to rotation. So this is something we don't have in our planet. So our magnetosphere is described very well with a dipole. So the first part of the talk will be a small tutorial. How can you construct a model of the magnetosphere of Jupiter and Saturn to overcome this bad prediction that the dipole approximation gives? So first of all, let's see what's so special about the magnetosphere of Jupiter. As I said, the dipole approximation is not valid. It's only valid actually very close to the planet, up to maybe 8, 10 planetary radii. And also Jupiter rotates extremely fast. One day in Jupiter is half a day in Earth, actually around 11 hours. So this means very strong centrifugal forces. And also Jupiter and Saturn have some additional plasma sources. In the case of Jupiter is the volcanic moon Io, who constantly ejects material in the magnetosphere, around 500 kilos to 1 ton of material per second. Again, this is something we don't have as an equivalent on Earth. Our moon is pretty stable and quite boring in that sense. So the realistic picture that we want to model and create with our method is try to find what happens when you have a very rapid rotator like Jupiter and additional plasma sources. The answer is that the plasma is then confined near the equator, and the magnetic field lines are stretched, and they create what we call a magnetodisc structure. You can already see how the dipole lines are distorted in this region, in the middle magnetosphere. Now, there are many ways to do it. It's not the only method, it's a method, but it comes from first principles and uses spacecraft data, so you can get a nice global overview of the magnetosphere of Jupiter. The theory is quite old. It's from the late 80s, and quite recently, the group at UCL created a code that implements this theory in Saturn and then in Jupiter. And recently, we had an updated version that I'm going to explain how we implemented newer observations of Jupiter. So let's dive into the theory. Of course, we have to restrict the problem to be able to simplify our calculations. We assume an axisymmetric model, and we only choose the meridional plane, so a cut perpendicular to the orbit of Jupiter. And now we have to consider the dominant forces in the system. Of course, the magnetic force, J cross P, of course, the gradient of the plasma pressure, including cold plasma and hot plasma. Again, I remind there is no hot plasma equivalent in the terrestrial magnetosphere, or not as significant. And of course, the centrifugal force, because Jupiter is rotating extremely fast. Now, you may ask, where is the gravity? Indeed, Jupiter is really massive, but the gravitational force is quite weak compared to all the other forces. Actually, after 2 or 3 Jovian radii, is no longer important. Now, since we're working in an axisymmetric case and taking into account that the magnetic field is solenoidal, we can use a trick to express the magnetic field in the so-called Euler potentials. So basically, you write the magnetic field as the cross product of 2 gradients. These alpha and beta are called Euler potentials, and this is what we're going to use in the following calculations. Again, I remind we have to take into account the hot plasma population in our system, and then to close up everything, you need some constraints from observation. Basically, the temperature, density of the plasma, the composition of the plasma on the equatorial plane, so you can start to do your iteration with a code and produce a model. Then you also need the angular velocity of the plasma on the equatorial plane. The first approximation in the original work from the 80s was according to Hill's theory. So basically, you calculate the angular velocity as a function of distance, assuming you have a magnetic dipole on the planet. So again, as I said, the theory behind the code is quite old. So the first observations were quite old, basically from the Voyager era. So the first thing we did is try to find some newer data. We used data from Galileo. So on the left, the yellow line shows the first approximation in the original theoretical model using Voyager data. It's not very clear now with these scales, but it's a series of piecewise linear functions, which of course it's not smooth. The newer Galileo data are shown in blue squares, and the analytical fit is the solid blue curve. So this is what we implemented in the code. We can have either Voyager data or Galileo data as initial conditions. Just a small pause here. Why is this important? It's important because when you compare the hot plasma content of the magnetosphere for these 2 very different eras, you find that the Galileo observation, the red one, is actually quite depleted. So when Voyager visited Jupiter tens of years ago, the hot plasma pressure was really important, but Galileo in the early 2000s showed something really depleted. So we kept both conditions in the code, and we can model two very different eras of the system. And of course, if you know the temperature and the hot plasma pressure, you can also find the density and other quantities on the equator. Then the last ingredient was the angular velocity of the plasma. This was given, if you consider again a dipole, by this equation. Here, the important parameters are L, so the equatorial crossing distance, or the distance along the equator, and the corrotation lag F. This F quantifies how much slower the plasma is rotating compared to the angular velocity of Jupiter. And L0 is a parameter that just scales the distances to planetary units to have a nice reference point. I will also highlight this parenthesis here. This is called the mapping function. Basically, it's a recipe that connects a point on the equator with a point on the ionosphere of the planet. For a dipole, it has this very simple form as a function of L, but as I'm going to show you later, this is not always the case. Now, before I explain the plots, intuitively, if you're close to Jupiter, you expect the planet to impose the rotation on the plasma because you're very close to the ionosphere, magnetic fields and currents are really strong. And as you go farther away, you expect this to decay slowly. And this is exactly what this theoretical, again, model is showing. Up to 6 Jovian radii approximately, the angular velocity of the plasma is more or less equal to Jupiter's, but if you go to larger distances, it follows an asymptotic form that respects the conservation of angular momentum. All right, then we have everything we need. We can now calculate the magnetic field of Jupiter and the profile of its magnetosphere. The calculations are performed in a numerical grid in spherical coordinates. R is the radial distance and cosine of theta is the cosine of the colatitude. We start with a magnetic dipole and we perform iterations trying to optimize the solution and come closer to a realistic profile. Again, we are very lucky because we are using axisymmetry. So one of the two Euler potentials, this potential beta, can be thrown away because it's just a constant if you go around the planet in the phi direction. And this is really helpful because everything can be expressed through the other magnetic potential alpha. So the magnetic field, plasma density, pressure, temperature, everything is a function of alpha. So basically you just have to calculate one quantity. And then it's just a matter of choice how precise you want to be. And we selected typically that if the iteration at the step I produces less than 1% error compared to the previous step, then we're satisfied with the solution. Now, a comparison. This is the theoretical model from the original paper in the 80s, and this is a sample solution using the new Galileo conditions. The solid lines are the magnetic field lines, assuming that the magnetic field of Jupiter is a dipole, and the dust lines are the more realistic magnetodisc profile. If you go close to the planet, you see that these two lines coincide. This means that the magnetic field is more or less a dipole near the planet, but if you go at larger distances, it is really stretched and deviates from this description. And just to justify the name magnetodisc, I will do a trick now. I will calculate I will subtract the dipole contribution from the total magnetic field potential. And you can see that all these additional contributions due to the hot plasma, the strong azimuthal currents, the centrifugal force are really located in the middle magnetosphere and confined near the equator. Okay, and this is a spot that we're really happy. We have something that is consistent with the observations. The predictions about the magnetopoles are more or less correct, again, compared with the observations. But we went one step farther because at the end of this process, the magnetic field we calculated and the angular velocity are no longer consistent. Remember, we started with a magnetic dipole, so the angular velocity was consistent with the magnetic dipole, but we have something which is clearly not a dipole anymore. So there is a small solution to this problem from the late 90s and early 2000s. There were different groups that stated, okay, if you have a magnetic field, in this case a magnetodisc, or something which is not a dipole, you can use this updated information to correct your solution for the angular velocity. So it's exactly the same equation that I showed before, but now you notice that there is, instead of this nice functional form that connects the equatorial plane with the ionosphere, there's a more different, more difficult form. So first of all, as I mentioned, the mapping function, so this recipe to connect magnetic field lines is more complicated. And there is also this new B factor, which is a clever way to quantify the divergence from the dipole. It contains two terms for the radial magnetic field and for the perpendicular component. Again, we're a little bit lucky because the radial divergence of the magnetic, well, I should say the radial deviation from the magnetic field is calculated very close to the ionosphere. But as we said before, the magnetic field very close to the planet is a dipole, so we can disregard this term. The other term, however, is quite important. I showed you before that if you go at larger distances, the magnetic field profile is very different compared to the dipole. So we performed the same exercise again, but now we don't do a numerical relaxation on the magnetic field, but a numerical relaxation on the magnetic field and the angular velocity. So the idea is, first, you take your initial conditions, you calculate the solution for the magnetic field, you feed this solution back to the code, and you calculate an improved solution for the angular velocity, and you do the same trick again until both quantities are at a threshold that you consider like appropriate for your solution. Again, we assume that if during the iteration the relative change is less than 1%, we have a very good approximation of the magnetosphere. And just to show you how much the angular velocity changes through these iterations, the black line and the red circles are the original angular velocity according to a dipole solution. But if you perform this extra numerical iteration of the angular velocity, you have the blue curve that you can see very close to the planet, and maybe in the middle magnetosphere is not that much different. But if you go at larger distances, it really deviates a lot. And on the right, you can see how this solution is slowly updated with every iteration. Now, the reason we are interested in this very precise description of the angular velocity is it's because it affects the centrifugal force. And if the centrifugal force changes, the whole force balance changes. So in order, you need to really have these two in a consistent way. So this is the tutorial part of the phase. So if you have any questions up to this point, we can answer that.
So the point of the tutorial phase is to use first the normal, I think you said, Hill equation, get the solution to the dipole, and then make again with the modified Hill equation, so that you iterate over the velocity field. Is that the general idea?
Yes.
What exactly data you're using for the model? You showed something from the Voyager, like some plots, but it was like some dimensional temperature.
So you need density, temperature, but these are connected for the models, and the hot plasma pressure. And the angular velocity you originally take from Hill's theory. You can also use data, but normally the plasma data are not very well constrained. But yeah, for the equatorial conditions, you need density or temperature and angular velocity. Okay, so the second part is some applications that we worked on using this magnetodisc code. The first task was to determine the compressibility of the magnetosphere. Now, what is really interesting about Jupiter is that it can undergo really dramatic changes in its size, the size of the magnetosphere. And according to some simulations, statistically, we found that this magnetosphere can be preferably found in an expanded state with a typical size of 90 Jovian radii, or in a compressed state with a typical size of maybe 60 Jovian radii. Of course, the magnetosphere can be found in between, but statistically, these are the two most probable states. And of course, this is a huge difference, and we wanted to see if we can understand how this compression happens and also compare it to the Earth and Saturn. So first of all, why does this compression or expansion happens? Because, of course, the solar wind changes, the interplanetary magnetic field changes, and also for these systems like Jupiter and Saturn, we may have some internal changes like the hot plasma content. Again, there's no really equivalent for the Earth because we only feel the change due to the solar wind. And how do we do this? Since we are assuming force equilibrium to determine the magnetopoles, we're trying to see how the magnetopoles changes if the solar wind conditions change. Of course, this is not very easy because we don't have enough data for Jupiter to find all these pairs of magnetopole size and solar wind conditions. So what we did is we created a very big ensemble of models, around 600 models of the code with different magnetopoles radii and different hot plasma content. This sort of represent the different states of the magnetosphere, and since we're assuming pressure equilibrium, also the solar wind conditions. And just to find a number to quantify if the magnetosphere can be compressed easily or not, we use the compressibility index, which sort of measures how the magnetosphere responds to any change in any internal or external condition. Just to give you an idea of what kind of numbers we expect, if you have a dipole in vacuum, the magnetosphere that it will create has an index of 6. So typically we're expecting something lower than 6. So let's see this with a plot.
How this is defined?
Okay, I have a back slide. You assume that the magnetic pressure from the dipole field is exactly equal to the solar wind dynamic pressure. And since the magnetic dipole decays as 1 over r to the third, the magnetic pressure is squared, and this is the index that you use. So every dot on this plot is a different model of the magnetosphere with a different size and external solar wind conditions. This is the dynamic pressure that I have on the x-axis, and every different color has different hot plasma content. The warmer the color, the more hot plasma you have in your magnetosphere. To understand how this transition happens, we assume that the dynamic solar wind pressure is exactly balanced by the plasma pressure and the magnetic pressure inside the magnetosphere. Now, ideally, this compressibility index, if you have a log-log plot, will follow a linear or quasi-linear behavior. And as I'm going to show you, this is true for Saturn. But if you use your imagination a little bit, you can see the same for Jupiter. Let's choose your favorite color of blue. And if you try to model a linear fit, you can see that it seems reasonable. If you follow, let's say, a yellow color, it seems that the dynamic pressure changes linearly with size in a log-log scale. Unfortunately, Jupiter and Saturn are a little bit different in that sense. And if you do some higher order fitting, not just a linear fit, you will see that the compressibility index changes dramatically with size. The dashed horizontal lines are the compressibility values that we obtain just from the linear field. And as you see already, they're lower than 6, sorry, which means that the magnetosphere of Jupiter is more easily compressed than a magnetic dipole in vacuum. And also you see that depending on the hot plasma content, you have a very different behavior. And the next thing you see if you follow the curved lines is that there is an effect of the system size. So the compressibility of a magnetosphere with a specific hot plasma content changes with size. So if you take the exact same hot plasma content and you just increase the size of your magnetosphere, the compressibility index will change. This is something we do not have on the Earth, and this is something that we do not observe also on Saturn. And this is an effect just because of the magnetosphere of Jupiter has an enormous size. And just to prove what I was saying before, one of our PhD students did the same exercise for Saturn. And she found that there are two profiles for the compressibility index, for an expanded state or a compressed state, the same as we are using for Jupiter, but they both follow a linear profile. And there is a specific value for the compressibility index that changes according to the external conditions. This is something we did not observe for Jupiter. If just with a linear analysis, you need to dive deeper into second order fitting to find some effect of the system size. The second application we worked on was particle motion in the planetary, in the magnetosphere of Jupiter. And we examined the charged particles that move under the effect of the Lorentz force. The basic motion is quite similar to the one we know in the terrestrial magnetosphere. If you have a charged particle, it will bounce back and forth between two mirror points. And you can quantify its motion using the gyro radius and the pitch angle, so the angle between the velocity and the magnetic field. And on Earth, we are quite lucky because usually what we call the adiabatic approximation holds. So if you have a magnetic field that does not change significantly either with time or with distance, then you have analytic solutions that you can use to define the motion of these particles. However, we are not so lucky with Jupiter. First of all, we have different kinds of plasmas. We have protons and electrons, of course, but we also have oxygen and sulfur ions from the volcanic moon Io. So using the magnetodisc code that I described before, we take one of our favorite models and we initialize charged particles at different locations with different energies and different pitch angles. And we wanted to see, is this approximation, is the adiabatic motion valid, under which conditions? And these results are very interesting for people doing auroral studies or particle precipitation in different moons. So what we found, let's say for a proton, is that if you have a very cold proton, a proton with very low kinetic energy, the motion is as you would expect in the magnetic field of the Earth. So the particle will just bounce happily back and forth in the magnetosphere, and the pitch angle as a function of time will just be a periodic function with the same value every time that the particle crosses the equatorial plane. If you increase now the energy of this particle, you will see that the trajectory starts to thicken a little bit. This means every time the particle crosses the magnetic equator, its pitch angle changes a little bit. So basically, every time it crosses the equator, it follows a slightly different trajectory, and it's not symmetric anymore. And if you increase the energy even more, every periodicity in the pitch angle is lost, and as you can see, the trajectory is no longer symmetric. This means that under some conditions, this particle may go very close to Jupiter, and then it may follow some local electric fields and be accelerated all the way into the atmosphere of the planet and produce auroras. Or if it passes close to one of the moons, let's say Ganymede or Europa, again, it can fall and effectively lose the particle. Now, what is the idea behind this? The answer is that this is entirely an effect of the magnetodisc field. the fact that we don't have a nice dipole changes the dynamics in the middle magnetosphere. I haven't found a good way to explain this except these not very nice plots. I have again the same proton with different energies. The dust line is the curvature, the radius of curvature of the magnetic field line at which the particle is initialized, and the blue crosses are values of the gyro radius of the particle with time. So time in this plot flows upwards. Now, for the very cold cases, so protons with very low energies, you can see that the gyro radius of the particle, every time it crosses the magnetic equatorial plane, is the same. So in this case, the motion is adiabatic. The particle just bounces back and forth at the mirror points. If you increase the energy, you see that there are crosses appearing at higher values, which means that the gyro radius of the particle starts to increase with time. Every time the particle crosses the magnetic equator, its gyro radius increases, and so forth at larger energies, and at some point it becomes comparable to the local radius of curvature of the magnetic field line. What does this mean? It means that the adiabatic approximation, so what we had in mind that the magnetic fields do not change extremely with time or distance, is no longer valid, because the gyro radius of the particle, of a very energetic particle, is so large that basically it crosses multiple magnetic field lines. So you're crossing regions with very different magnetic fields. And this is something that happens in Saturn or Jupiter or a planet with a non-dipolar magnetic field. Any questions so far before I move to the spatial missions? Okay. So the European Space Agency and NASA have some missions planned for the Jovian system. The second one, but the first one to arrive, which is a little bit unfair, is Europa Clipper. As the name suggests, it will be focused entirely on the moon Europa, which is an icy moon. And what is interesting about Europa, first of all, you notice these cracks on the surface that people working on the field believe it's an effect of the gravitational forces of Jupiter, and it's an energy source. And there are also plumes of water and ice that were detected by previous missions. So the current model we have for Europa is that it's a moon with an icy crust and a liquid water ocean buried under this crust. And actually the amount of water that we believe Europa hosts is twice as much as all the oceans of the Earth combined. So it's a huge amount of water, and it's also potentially a habitable world. So NASA invested a lot in this mission. But ESA launched first another spacecraft last April, JUICE, which is going to explore the Jovian system, Europa, Callisto, and the primary target will be Ganymede. All these satellites are believed to have a similar structure in the sense that maybe they have a subsurface ocean as well. But the primary target for habitability is Europa. And what I find a little bit terrifying is that after the end of its mission, so towards the end of the mission, JUICE will be the first ever satellite to orbit a moon other than our own, but it will crash on Ganymede, which is, well, according to the mission planners, there is no much danger because the ice crust on Ganymede is quite thick. We don't expect any contamination, but still, it's a potentially habitable world, and there are easier solutions to get rid of this spacecraft. Now, why is Ganymede so important? This is a time series of magnetic field measurements of Juno, and you can see that close to its trajectory at 15 Jovian radii, there's suddenly a spike, which is not predicted by any model. This is the signature of Ganymede itself. So Ganymede is the only moon we know so far in the solar system that has its own magnetic field. And we believe it has, to a first approximation, again, a dipole shape. And this is a plot of our master student, Alex. who compared the Juno data in red and the magnetodisc model that I showed you, in black, and the magnetodisc model in red. And he added a small dipole contribution at the same location where Ganymede was during this encounter. And you can see there is some agreement with the data if you include this additional magnetic field. However, there is some discrepancy, as you can see, at larger distances. And this is because the magnetic field of Ganymede is not so easily described as a dipole. Of course, it has a dipole component, but at the same location, you have an effect from the magnetic field of Jupiter. Just to give you an idea of the scales, this entire magnetic field is located in this tiny region around 15 Jovian radii. And to make things even more complicated, I mentioned there is a subsurface ocean inside Ganymede. This subsurface ocean, we believe there it has some minerals that are dissolved, which means it's conductive. And since, of course, nature doesn't care about aligned rotation axis and magnetic axis, and there is a small angle between the two in Jupiter, what basically happens is that the magnetodisc during one rotation flaps up and down from Ganymede. What does this mean? There is a temporal change in the magnetic field, which means there is an induced response from Ganymede. So, what hopefully JUICE will observe is some diagnostics to try to constrain the composition of this subsurface ocean and study the induced magnetic field. Maybe there's something similar in Europa, but so far we haven't detected any similar signatures as in Ganymede. Okay, and to summarize, in order to model the magnetic field of Jupiter, we saw that there is no adequate description using a magnetic dipole. So we used a theoretical model from the 80s and made it into a code that calculates the magnetodisc of Jupiter using different conditions, Voyager or Galileo, and we're still expecting the plasma data from Juno to incorporate also this in the model. As we saw, it's a very different world compared to the Earth or Saturn. This is evident from its compressibility. Just the sheer size of Jupiter makes things more complicated. And our predictions are quite normal regarding the compressibility index, but we have to verify them using different crossings from Juno. Again, we need some plasma data to be exactly correct in our comparison. The second application was the motion of charged particles in this system, which is, again, very different compared to the terrestrial case because of the magnetodisc. You have a magnetic field that changes very rapidly with distance, so the motion of the particles is no longer adiabatic. And it's a system that it really has many more things to explore. As I mentioned, 2 space missions, one on its way and one that will be launched next year around this time, studying the icy moons of Jupiter. And that's it. Thank you very much.
Έχουμε 10 λεπτά.
Σε τι γλώσσα είναι?
Τώρα είμαστε όλοι Έλληνες είμαστε εδώ, που βλέπω, ενώ ελληνόφωνες. Ό,τι προτιμάμε.
Τέλος πάντων. Στο δεύτερο το section, εκεί προς το τέλος, έδειξες ότι άμα είναι πολύ ενεργειακό το πρωτόνιο, δεν έχει κάποια. Δεν είναι περιόδικο όμως, τέλος πάντων, και κάνει πάρα πολύ εκεί πέρα. Και έδειξες ότι στο γράφημα είναι πάρα πολύ το zero rate. Αυτό σταματάει κάπου, ας πούμε, θα έχουμε ejection των particle.
Σταματάει αν κάποια στιγμή το σωματίδιο πρωτόνιο ή οτιδήποτε άλλο, τα ίδια ισχύουν και για τα ιόντα, θείο κτλ. Αν φτάσει πολύ κοντά είτε στο Δία είτε σε κάποιο από τους δορυφόρους, που εκεί πλέον το μαγνητικό πεδίο δεν είναι τόσο απλό, μπορεί να υπάρχουν και ηλεκτρικά πεδία που να το επιταχύνουν και να χαθεί.
Αφαίρει το σύστημα.
Ναι, φεύγει το σύστημα.
Δηλαδή αυτό θα μπορούσε να το μετρήσει κάπως. Έχω ένα constant emission, ας πούμε, από υψηλό.
Αυτό που έχουμε συζητήσει με έναν συνάδελφο ο οποίος δουλεύει πάνω στο ΣΕΛΑΣ, στο Δία, είναι να κάνουμε μια στατιστική μελέτη με κάποια κατανομή σωματιδίων που έρχονται από μεγαλύτερες ακτίνες. Κάποια ιόντα θείου, ας πούμε, ξεκινάνε από 60 ακτίνες Δία. Τι ποσοστό από αυτό τελικά θα φτάσει κοντά στο Δία ώστε να δώσει σέλας. Και αν αρκεί αυτό το ποσοστό για να δούμε τη λαμπρότητα που παρατηρούμε. Επίσης, επειδή υπάρχουν άλλα γκρουπ που μελετάνε την πρόσκληση σωματιδίων σε δορυφόρους, ας πούμε στην Ευρώπη, μπορεί πάλι κάποιος στατιστικά να δει από μια κατανομή τι ποσοστό θα καταλήξει στην Ευρώπη.
Στο ίδιο θέμα, έδειξες ότι στα πιο ενεργητικά σωμάτια, τα οποία ακολουθούν όχι την καθαρά συμμετρική τροχιά, η γυροακτίνα αυξάνει τον χρόνο. Οπότε αυτό πώς το εξηγείς, ότι δηλαδή τι προσδίδει ενέργεια στο σωμάτιο για να αυξάνει τη γυροακτίνα με τον χρόνο, δεδομένου ότι μετράς την γυροακτίνα φαντάζομαι στο ίδιο πάντα σημείο που το μαγνητικό πεδίο είναι.
Μετράμε τη γεωακτίνα στο σημείο που το σωματίδιο περνάει το σημερινό επίπεδο. Οπότε διασχίζει, ναι, δεν κερδίζει ενέργεια, απλά διασχίζει διαφορετικές περιοχές. Ναι, η μαγνητική γραμμή ήταν πιο πολύ για σύγκριση με την αρχική τροχιά που είναι συμμετρική.
Η ανομαλία του μαγνητικού πεδίου παρατηρείται στο Γανιμίδι. Στους άλλους δορυφόρους δεν παρατηρείται ότι η Europa είναι πιο κοντά και στο μαγνητικό πεδίο.
Όχι, η ΙΟ δεν έχει μαγνητικό πεδίο, όπως ο Ξέμ που είναι ο κοντινότερος δορυφόρος. Η Καλιστό είναι αρκετά μακριά, πάλι δεν έχει παρατηρηθεί κάτι. Τώρα, το μοντέλο για το επαγόμενο μαγνητικό πεδίο που έδειξε για το Γανιμίδι θεωρητικά ισχύει και για την Ευρώπη, αλλά δεν έχει παρατηρηθεί κάτι. Οπότε, γενικά στο Γανιμίδι πιστεύουν ότι υπάρχει, ακόμα και αν δεν υπήρχε ο υπόγειος. Ναι, είναι ακριβώς. Ναι. Ακόμα και να μην υπήρχε ο ωκεανός που θα επάγει το μαγνητικό πεδίο, θα είχε το δικό του δίπολο. Αυτό έχει μετρηθεί, τουλάχιστον.
Στην πρώτη ανάλυση που έδειξες, το μαγνητικό δίπολο του Δία θεωρείται σταθερό ή θεωρείται ότι υπάρχει μια χρονοτζάτηση εσωτερική?
Θεωρείται σταθερό γενικά.
Τι είναι?
Από όσο έχουμε μετρήσει, ναι. Δηλαδή, από τροχές που περνάνε κοντά από το Δία δεν έχει φανεί κάποια μεγάλη μεταβολή, ως προς το δίπολο τουλάχιστον. Βέβαια, είναι λίγο δύσκολο να δώσω απάντηση με την έννοια ότι είναι πολύ μεγαλύτερο σύστημα και μπορεί να υπάρχουν τοπικές ανομαλίες στο μαγνητικό πεδίο. Αλλά ο διπολικός χαρακτήρας είναι λίγο πολύ σταθερός.
Από ό,τι κατάλαβα, αυτές οι μαγνητόσφαιρες είναι αρκετά διαφορετικές κατευθύνσεις. Και μια από τις διαφορές είναι η θερμική πίεση, που είναι μεγάλη αρκετά και τοποποιεί.
Ναι, ότι υπάρχει ένας πληθυσμός σωματιδίων που δεν είναι cold για να γίνουν με HD μοντέλα.
Ωραία. Αυτό πόσο σύντομο μας την αλλάζει η υπόθεση ότι αγνοούμε τις κρούσεις και κοιτάς μόνο κίνηση σωματιδίων σαν να είναι μονομένα και. Δηλαδή και δεν είναι πλάσμα με την έννοια πολύ ζωντανό πλάσμα.
Αρκετά σίγουρα. Βέβαια, αν κάποιος θέλει να κάνει κλασική MHD, πρέπει να κάνει παραδοχές, οπότε συνήθως όλα τα MHD μοντέλα που κάνουν simulation δεν έχουν αυτό το θερμοπλάσμα. Οπότε από αυτή είναι κάτι χάνουν. Στη συγκεκριμένη θεώρηση υπάρχει ξεχωριστή εξίσωση για το θερμοπλάσμα, που πάλι εκφράζεται μέσω του μαγνητικού δυναμικού. Αλλά γενικά ισχύει αρκετά καλή προσέγγιση.
Ποιος ελέγξει δηλαδή ή έχει μετρήσει τη βιογραφία?
Ναι.
Ήταν ενδιαφέρον που έδειξες ότι το hot plasma content αλλάζει μέσα σε μια δεκαετία ή σε 15 χρόνια. Αυτό το time scale είναι αρκετά μεγάλο σε σχέση με το time scale που χρειάζεται για να επέλθει κάποια ισορροπία στο σύστημα.
Είναι αρκετά μεγάλο, δηλαδή οι αλλαγές, άμα υπάρχει κάποιο compressibility, είναι, αν θυμάμαι καλά, τάξεις κάποιων ημερών ίσως. Οπότε δεν επηρεάζει τόσο. Θα έχει ενδιαφέρον όταν βγουν τα δεδομένα από το Juno, γιατί δεν υπάρχουν ακόμα. Υπάρχουν δεδομένα για μαγνητικό πεδίο, δεν έχουν βγει στο κοινό τα δεδομένα για το πλάσμα, να δούμε σε τι κατάσταση είναι τώρα.
Ο Γανιμίδης είναι πηγή πλάσματος, επηρεαστικά.
Ο Γανιμίδης δεν είναι πηγή πλάσματος, τουλάχιστον όχι σημαντική όπως η ΙΟ. Επηρεάζει πολύ λίγο, δηλαδή η μαγνητόσφαιρα του Γανιμίδη έχει πολύ μικρό μέγεθος, δηλαδή μία ακτίνα βία, ίσως βασικά πολύ λιγότερο. Ας πούμε ότι είναι 14,8 με 15,2 ακτίνες δία, είναι πολύ μικρότερο. Οπότε είναι μια πολύ μικρή μαγνητόσφαιρα μέσα σε μια μεγαλύτερη. Ωστόσο, είναι αρκετά πιο πολύπλοκη και από αυτό που έδειξα εδώ, γιατί εφόσον υπάρχει μια μαγνητόσφαιρα, υπάρχουν και ρεύματα στη μαγνητόσφαιρα, οπότε υπάρχει επιπλέον συνεισφορά στο μαγνητικό του πεδίο. Αλλά στο γενικότερο μαγνητικό πεδίο του Δία δεν έχει συνεισφορά.
Η διάσκηση του μαγνητικού πεδίου σε σχέση με τον Γανιμίδη, εδώ πόσο μακριά είναι, δηλαδή το σημείο που διασχίζει την τροχιά του Γανιμίδη, σε σχέση με το που βρίσκεται το Γανιμίδη στην τροχιά.
Σε ακτίνες Γανιμίδη, ο Γανιμίδης ας πούμε, είναι λίγο μεγαλύτερος από τον Ερμή, για να έχουμε μια τάξη μεγέθους. Αρχίζει να φαίνεται το δίπολο του Γανιμίδη σε περίπου 3-4 ακτίνες Γανιμίδη. Οπότε είναι πραγματικά σε μια πολύ μικρή περιοχή.
Οπότε αυτό που βλέπουμε εδώ είναι πέρασμα κοντά.
Ναι, είναι πολύ κοντά. Αν θυμάμαι καλά, είναι σε περίπου 2,7 ακτίνες Γανιμίδη.
Σε σχέση με τη σύγκριση των πιέσεων που μέτρησε το Voyager και η άλλη αποστολή, είμαστε σίγουροι ότι μετράμε την ουρά.
Όχι ακριβώς. Μετράνε μεν θερμότερο πλάσμα, αλλά έχουν διαφορετική ευκρίνεια και στα κανάλια που κοιτάνε στην ενέργεια και στην ακρίβειά τους.
Οπότε δεν είναι τόσο μεγάλη διαφορά.
Τον Γαλιλαίο, επειδή ήταν νεότερη αποστολή, είχε καλύτερη ακρίβεια γενικά, οπότε είμαστε σίγουροι ότι υπάρχει διαφορά. Το αν είναι ακριβώς η ίδια, θα δούμε από το Jovian. Αλλά ακόμα και αυτά τα προφίλ του θερμού πλάσματος είναι από fixed δεδομένα, οπότε έχουν ήδη κάποια προσέγγιση.
Δεν είναι απλά θέμα σφάλματος, είναι ένα bias.
Δύο τάξεις μεγέθους.
Ναι, δηλαδή αυτό δύσκολο μπορεί να το εξηγήσει από ένα calibration έργο. Να έχεις την τάξη μεγέθους. Μπορεί και όμως.
Και εγώ αναρωτιέμαι, όταν λένε πίεση, πώς το μετράνε, τι κάνουν στο κατρέπεις και πώς σε πίεση.
Ναι,
Είναι άλλος
μετράνε.
να μετράνε άλλο σωματίδια.
Ναι, πρέπει να είναι καλυπαρισμένο.
Σίγουρα μετράνε διαφορετικά σωματίδια, γιατί έχουν διαφορετικές πυκνότητες και ενέργειες ανά ιόντα και ανά ενέργεια και βγαίνουν διαφορετικά fit. Οπότε σίγουρα υπάρχει μια τέτοια.
Δηλαδή, μπορεί να παρατηρείς κάποια σωματίδια σε μια μπάντα ενέργειας και κάνεις extrapolate. Δεν ότι ισχύει, άμα δεν βλέπεις την ίδια μπάντα σου, την ίδια μπάντα ενέργειας.
Καινούργια αποστολή στον οποίο τουλάχιστον κάτι κοινό με τα προηγούμενα, την ίδια παρόμοια μυθολογία.
Ελπίζουμε πως ναι. Ακόμα δεν έχουν βγάλει τα δεδομένα.
Ναι, αλλά οι ανιχνευτές, η μεθοδολογία, αυτά που χρησιμοποιούν.
Νομίζω είναι πιο συναφή με τον Γαλιλαίο.
Με τον Γαλιλαίο, οπότε θα δούμε.
Κάτι σχετικό πάλι με αυτή που εφηγήσουμε η θερμοκρασία η οποία μετράται είναι ίδια για όλα τα species των ιόντων ή μπορούμε από αυτές τις αποστολές να μετρήσουμε θερμοκρασία διαφορετικών ιόντων. Γιατί υπάρχει ίσως την ερώτηση κατά πόσο επέφυγε και η θερμική ισορροπία, γιατί είναι ισόθερμο αυτό το hot plasma.
Από ό,τι θυμάμαι, στον Γαλιλαίο πάλι από αναλυτικά φύτα έχει προέρθει, και το οποίο μάλιστα φύτα δεν ισχύει για όλη τη μαγνητόσφαιρα, ισχύει σε συγκεκριμένα σημεία. Νομίζω από 10 μέχρι 30 ακτίνες Δία και μετά έγινε ένα extrapolation και εμείς προσθέσαμε ένα extrapolation προς κοντά στον Δία, οπότε μετράνε και διαφορετικά ιόντα, δηλαδή σίγουρα ακόμα και στη θερμοκρασία μεταξύ Voyager και Γαλιλαίο έχει σημασία το ότι ήταν διαφορετικά όργανα.
Θεωρούμε ότι τα διαφορετικά ιόντων έχουν την ίδια θερμοκρασία.
Νομίζω πως ναι. Τώρα, ως προς το αν είναι το θερμό πλάσμα διαφορετικό σε αυτές τις δύο εποχές, επειδή παρατηρούσαν και διαφορές στο δαχτυλοειδές ρεύμα, υποθέτουν ότι όντως υπάρχει διαφορά, αλλά είναι το πόσο μεγάλη είναι ακόμα ανοιχτό.
Άλλη ερώτηση. Αν όχι, ευχαριστήσουμε τον Δημήτρη. Και θα προσπαθήσουμε να έχουμε κι άλλα δύο σεμινάρια, οπότε έχουμε την ευκαιρία να σας ενημερώνουμε.